Hello guys, so this is the first video in 7.3 angular motion. In this video we're going to address C4, axes of rotation. You'll already be familiar from anatomy the planes of movement, and these axes kind of go in partnership with those, and the principles of angular kinematics. And again in 7.1 we learnt about linear kinematics. So what do you remember from 7.1 linear motion? You made videos to explain and explore different linear motion concepts. So hopefully you'll recognize that there was distance displacement, there was speed velocity, and there was acceleration, all based on linear motion. Well, the good news is you understand, therefore, the bases for angular kinematics, because we need to look at those same principles, but in terms of angular motion rather than linear motion. So what is angular motion? Angular motion is motion about a body which twists or turns about this imaginary axis. And we're going to look at those three axes you need to know in a moment. We will then study the different angular kinematics, so angular velocity, angular acceleration, and angular distance or displacement. Later in this assignment, you'll also learn about angular kinetics. So 7.2 was about the forces that generate motion, and we will look at the forces that generate angular motion, that allow objects to pivot around these axes. So all of these concepts actually you've pretty much addressed before, and what we just need to do is apply this understanding to angular motion. So the language will be very, very similar. So revision from anatomy. What do you remember in terms of the planes? So this movement here is obviously abduction and adduction. Hopefully you'll remember what a plane is. It's an imaginary flat surface that movement happens in, and there are three planes of motion. So we've got the plane of motion that abduction and adduction happens in, and I'm sure you'll remember that's the frontal plane, like your star jump. You'll also remember the sagittal plane, where flexion and extension happens in all joints. And of course the third plane is the transverse plane, where all rotational movements will happen in. This one happens to be horizontal flexion and extension. What we need to do is pair those, however, with axes, because movements happen around either a real or an imaginary axis. So what is an axis? An axis is a rotation. An axis of rotation is an imaginary or real line about which the body rotates. The whole body or limbs, of course. So here's our frontal plane up here. Now, in order for abduction and adduction to happen at the shoulder joint, what we've got to imagine is an imaginary axis running from front to back through the shoulder joint. If I had a massive skewer and I stuck it through this person's shoulder from front to back, then that would be the anterior posterior axis that the arm rotates about. So the frontal plane and the anterior posterior axis are kind of paired, that plane and that axis. The same would be true of the legs. So abduction at the hip is obviously lifting the limb away from the midline. What we need to imagine is if I had a massive skewer and I stuck it through front to back through this person's hip, then that limb can rotate around that axis. So frontal plane, anterior posterior axis. Then we've got our sagittal plane, so flexion and extension. In order for, let's say, our elbow or our shoulder for that matter to flex forwards or extend backwards, we need an imaginary skewer going side to side through that joint. So if we're looking at flexion at the elbow, flexion extension at the elbow, we'd need an imaginary skewer going side to side through our elbow joint, or side to side through our shoulder joint, like this line is showing. So that's called mediolateral axis. From the middle, in fact, if you went from the middle to the lateral to the outer side, side to side, remember you've got medial and lateral sides to your knee. So it's the side to side axis, mediolateral axis and sagittal plane are paired, and they allow flexion extension to happen. which leaves us our transverse plane. Both these examples are the transverse plane. This one's a whole body, well, both actually are whole body. So if you had a massive skewer going down through this man's head, his torso, his trunk is rotating around that big imaginary vertical skewer. Similarly, if I had a massive skewer going down through this hammer thrower's body, they would be spinning around that imaginary axis. So we know rotation happens in our transverse plane, and this axis is the longitudinal axis. It goes the length of the body vertically. The longitudinal axis and the transverse plane are paired to allow rotation to happen at any joint or whole body. Okay, so we know what an axis is. It's an imaginary line. In my head, I picture a skewer going through the whole body or a joint, and it allows rotational movements around that joint and in specific planes, remembering that these axes and planes are paired. One must be to do with gymnastics activities or events. There are lots of events in gymnastics, and you must give at least one other, a different kind of sporting example of axes on the use of these three axes. You can just pause the video and have a look. That's just a summary table basically going through what I've just explained on the previous slide. And here is the summary of the specification that you can check your understanding through. Okay, so let's get on to the angular kinematics, motion, angular motion. Now the equivalent for us in 7.1 was distance and displacement. All we're doing is saying angular distance and angular displacement. The principles are exactly the same. So here's an example. If this person was holding the dumbbells at the bottom, this was 0, and they finished up here. It's not quite vertical, so they've moved through their sort of forearm at the elbow joint through nearly a whole but not quite a whole half movement, just going to the top phase. What would be the distance and what would be the angular displacement in degrees? So distance and displacement are in degrees. Well, if they were vertically pointing the dumbbells down and then managed to do a complete vertical upward movement, it would be 180 degrees, but it's not quite vertical. Therefore, I've put the distance as 160 degrees. What would the displacement be? Well, in this case, it's the shortest angle from A to B, and it would be the same. It would be the same. So displacement is also 160 degrees. But the principles are the same. Angular distance is how far does the person or the limb actually move. Displacement is what's the shortest distance between A and B. In this example, it happens to be the same. But what about if it was a complete repetition? So going up and coming down. What would be the angular distance for the up and down full repetition? So they move 160 up and 160 down, which gives us a total of 320 degrees total angular distance moved. And what would the displacement be? They go up, they go down, so they start and finish here. I'm sure you know the angular displacement would be 0. Okay, exactly the same principles. You guys will of course need to come up with your own gymnastics and other sporting examples. Here's a slightly more involved example. See if you can get your head around this. So, golfer starts with the club there, does a backswing, and then does, through these pictures, a forward swing to finish there. So that's the start position of the whole shot. That's the end of the backswing. That's the end of the forward swing. So I've used this sort of compass type diagram here to show. From there, they go up, let's call it 90 degrees up to there. Then they go swing all the way around and finish here. So going there, all the way around to finish there. What would the angular distance be? So we've got about 90 degrees there. We've got about 270 going around there. So that actually adds up to a total of about 360 degrees. That's the whole total angular distance covered. But what would the angular displacement be? Well, the start position is here and the finish position is here. Either way, the shortest route is about 180 degrees. So angular displacement is 180 degrees from start to finish. So just to summarize, these two terms that you should hopefully be able to grasp given your linear knowledge. Angular distance is the total sum of all angular changes, whereas angular displacement is the difference between the initial and the final positions. So if this pendulum went from there to there, that's the total distance, but actually it starts here, it finishes here, that's the angular displacement. Nice and understandable. Things get a little bit more involved when we look at angular acceleration because the unit of measurement changes. So when you're looking at angular position, as we just have been, then we talk about degrees. How many degrees is there in terms of change of position? But when we look at angular velocity or acceleration, so the time-related changes, then we have to use radians or radians. And you convert radians by dividing degrees by 57.3. Ultimately, I'll tell you what 1 rad is and you can use that. And we'll keep it really simple because this is very much above and beyond, to some degree, what you need to know. So any angular changes in position is degrees. Any time-related factors, so velocity or acceleration, is measured in radians per second. Here's an example. So a ski boarder jumps and rotates 4 times clockwise. Notice I specify a direction because it is a vector. Angular velocity and acceleration are vectors, as you know, around the anterior-posterior axis in the frontal plane, and they do 4 flips, so a quad flip. They do 4 rotations. So this is just actually showing off our knowledge of those planes and axes. This is good to include in your examples. Essentially, they're doing 4 360 degrees rotations. Now, 1 rotation of 360 degrees is 2.6 rads. So if they're doing 4, all you kind of need to do is times that by 4 by 6.2. 1 rotation is that, and they're doing 4 of them. What I'm also telling you is that it took them to do that quad flip, that 4 rotations, it took them 4.6 seconds. So 4 times 6.2 is the number of rads that they travel, and they took 4.6 seconds to doing it. Velocity is distance over time, isn't it? Sorry, velocity, yeah, it's displacement over time, I should say. This is how we calculate it. 4 times 6.2 over the time taken. So 4 times 6.2 is 24.8 over 4.6 gives us an angular velocity of 5.39 rads per second clockwise, because it's a vector. Take a moment, digest that. It's actually not as complicated. You know, the language is a bit annoying, but it's quite accessible. Here's another example. So a trampolinist does a seat drop. They obviously change the angle at their hips. They rotate their legs clockwise, 1.57 radians about the medial lateral axis in the sagittal plane. So they flex at the hip. That's how much they change that angle, and it takes them half a second to do it. What's their average angular velocity? So that over the time taken, the rads over the time taken, gives us 1.57 over 0.5 is 3.14 rads per second, angular velocity. Here's quite an interesting example. No calculations for you to do, but just a translation. So you may know that the hammer thrower starts from stationary, spins, 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 and releases. And obviously they're trying to generate angular velocity. They want to be rotating as quickly as possible at the release so that they send the hammer off. So there is angular acceleration. There is a change in velocity from the first rotation to the second to the third. And this graph actually shows that. So time is across the bottom in seconds. And here we've got the velocity, angular velocity, at the peak of the first rotation. And it's about 19 rads their rotation. So the velocity is, slower than the second rotation. Rads per second is probably about 23. And then the final rotation peaks at about 25. So they're going slower, faster, fastest, and then they release the hammer. Now the last angular kinematic principle is angular acceleration. Again, exactly the same principles. It's change in velocity over change in time. That was linear. This time we've got change in rads over change in time. So if for our ski boarder's rotation, we've already talked about him doing rotations, if his final angular velocity was 5 rads per second, his initial angular velocity was 3 rads per second, we do the change in angular velocity over the time taken. Here we go. So change in angular velocity is 5 minus 3, final minus initial is 2 rads. So it's 2 rads over the time taken. 2 rads over 1.3 is 1.5 rads per second squared, or rads per second. Again, it kind of feels a bit complicated, but it's not. You know what to do for linear. It's just the change in terminology. The principles are exactly the same. So here are definitions: angular velocity, the ratio of change of angular displacement, and the time during which that change occurred, and it's rads per second, the unit. Angular acceleration is the rate of change of angular velocity, and it's rads per second. It's basically change in angular velocity over change in time. Now, please remember that your examples must be from a variety of sports, but also you must include a gymnastics example for each of these biomechanical concepts. So 2 for each, 1 any sport using different sports, and 1 must be a gymnastics type activity.